All right, welcome back. So let us consider another example or set of examples on Leibniz formula. So look at this problem. This is given that 4 into x plus 1 the squared y the x squared plus 2 the y the x plus pi squared, this is pi not x, plus pi squared y equals 0. show that show that 4 into x plus 1 y n plus 2 plus 4n plus 2 into y n plus 1 plus pi squared y n equals 0. Okay, where y is differentiable of order n, okay, and yn, that's y sub n, is implying or means y sub n equals the ny, that's y sub n here is being used to represent the ny, that's the nth derivative of y. So when we come across it subsequently, we may not have this indicated, but we just know right now that this is another way to denote the n of y. All right, so let's go ahead and solve this problem now. We are given this relationship for y. We can see that this is second derivative of y, the squared y, the x squared. This is the first derivative of y. This is zeroth derivative, so to speak, of y. That's y itself. Okay. And now we're given this expression. We want to show this. So we want to show that this is true. So just look at this closely. You see that this is having second derivative. This is having yn plus 2. Okay, the coefficient here is the same as the coefficient here. The coefficient here is different from the coefficient here, but this is having yn plus 1. This is having y. This is having pi squared. The coefficients are the same. This is having y, but this has yn. So the point is that we can easily identify that from what we are given. Okay, so this is solution. I want to be writing solution now. I don't want to be drawing this line. So this is solution. Solve the problem. So then I will say that we're given this. This is what we're given. We're writing it out again. It is 4 into x plus 1. So the square y, the x square, that's the second derivative of y. We can write it as y2 or the square y. So the same thing, because we have been told that this notation means the ny. So if you write y sub 2, that is the 2y. All right. So then this will be plus 2y sub 1, then plus y, sorry, pi squared y. We're told that this is equal to 0. So now look at it. Comparing this with this, that is, this is where we're starting from, and this is where we want to go, or we need to get to. So comparing this with this, we see that this is n plus 2. That is, the y we have here is having the second derivative. This one is n plus 2 derivative, and this one is having first derivative. This is n plus 1 derivative. This one is having 0 derivative. This is having n derivative. So we see that we can possibly get to this point by taking the nth derivative of this equation. So if we take the nth derivative of both sides of this equation, then we expect that somehow we should get the nth derivative of y2. Okay, nth derivative of the second derivative, that will be the n plus 2 derivative, and this is going to give us something like this. So we can now take the nth derivative of both sides. That means we take the n of both sides. That will be the n of 4 into x plus 1 multiplied by y sub 2 plus 2y sub 1 plus pi squared y. Then this will be equal to the n, that's the nth derivative of 0. Of course, we know that will be 0, just to fill our righteousness, we just put that right there. And this is going to be, so we can separate this out. We know that the derivative of a sum of some functions is just equal to the sum of the derivative. So basically, this is 4, which is a constant. We can move it out. So this is going to be 4 into the n of x plus 1 of y2. All right. Then plus 2, which is a constant, so we can move it out, and then get the n of y1, then plus pi square. Pi square is a constant, it doesn't carry x, it doesn't depend on x, it doesn't depend on y also, so leave it out. Then this will be the n of y, and then this will be equal to 0. Derivative of constant is 0. So basically, what we now have to deal with is this, but we can simplify further a bit. This is going to be 4 multiplied by the n of x plus 1 y2. So we come back to this, then plus, so we can easily get what this is going to be. There's no further analysis to do for that. That is 4 into y into n plus 1. This is just like having something like this. We want to take the squared of, let's say, the cube u. That is just going to give you the 2 plus 3, that's the 5. So this will be the 5 of u. So that's the idea we're applying here. We know that this is the y. So if this is the y and this is the n, so the n multiplied by d, that will be the n plus 1 y. So basically that's what we are writing here, that this is the n plus 1 y. So this is representing the n plus 1 y. We know that y sub n is the n, so y sub n plus 1 is the n plus 1 of y. So that is that. And for this portion, we can write this also as pi squared, which is constant. Then the ny, we can just write it as y sub n, as we have been told in the question. And this will be equal to 0. So we are not at our destination yet. We don't have this to be equal to what we have been shown, or what we have been told to show. Okay, but we are close to it. We already have y into n plus 1, even though it doesn't have the coefficient that we seek. We know that we can still get there. We have pi squared into y sub n, that is here, and then we have this to be 4 into x plus 1 into y n plus 2. That is something like this. We are not sure of what this is going to be yet, because indeed this has to be simplified using the Leibniz formula, because y is a function of its own. We don't know what y is. Okay, whatever it chooses to be, it's not really our problem here. Y is a function of its own. Okay, it's a function of x. That's what we know. X plus 1 is another function of x. So basically, this has to do with us taking the nth derivative of the product of two functions. So because of that, we will have to do this using the Leibniz formula. So this is the issue now that we have to sort before we can now put it back in here and simplify our expression. So for this, we just identify this first to say that this one be equation A. So we'll come back to it. So basically, what we want to do to go forward is um, to find the n of x plus 1 multiplied by y2. So for this, we will say that let u be equal to, because this one is derivative will soon vanish, so let u be x plus 1 and let v be y2. Then going further, we say that the u will be equal to derivative of x plus 1, which is 1, and the v, that will be derivative of this, that will be y3. I mean, we have second derivative already. If you take the derivative again, that will be the third derivative. And then we're going to have this to be the what is this now, the squared u, and that will be derivative of 1, which is 0. And in this case, we're going to have the square v. The square v will be the derivative or the second derivative of the second derivative, or the derivative of the third derivative. That's the fourth derivative. Okay, And from this, since we already have this vanish, we can just generalize that this is going to be the n of u is going to give us 0, and that will happen for all n greater than or equal to 2. All right. Then for this, we can also identify that it keeps going on in that manner. So if we get to the n of b, we can see the difference between the number here and the number here is 2. So this is just going to be y into n plus 2. All right. So we have our results already. Then we add an additional page. This is this is everything we would need to substitute when using the Leibniz formula. So we can now use the Leibniz formula to obtain this. So we now say that by the Leibniz formula, we know that the UV the n of UV is meant to be the summation from r equal to 0 to n of n combination r the ru the n minus rv. So again, we expand this. We know that we just need the first few terms. This is just the first term and the second term. Okay, and anything going forward will be 0. So we don't need to do much here to get this result. This is going to be, so when r equals 0, that will be n combination 0, the 0, u, the n minus 0, v, and plus when r equals to 1, n combination 1, the 1, u, the n minus 1, b, plus the next one, when n equals to 2, n combination 2, the squared u the n minus 2v. So we know it's become 0 from this point. So let's leave it like that and just move on. So let's say that plus we know it will continue like that, but we're not really interested in the remaining because they are all going to be 0. Just let's just leave it this way, okay? And then this is going to give us the expression. We know n combination 0 is 1. We know that already from previous expansions. D to 0 is also 1. So basically what we have is u the n v plus we know n combination 1 is also going to be equal to 1. So basically what we have here will be um, that will be n combination 1, that is n factorial all over n minus 1 factorial 1 factorial. So that is going to be n into n minus 1 factorial. So that will cancel this. So we're going to have only n left here. So this will be n, okay, into the 1u, the n minus 1 b. All right. And the next thing, n minus 2 factorial, we know that is going to be equal to, that will be plus n into n minus 1, then divided by 2 factorial, which is 2. Then we have this to be the square u, the n minus 2v, plus, and so on and so forth. But then we know this will become 0, so this is just going to be equal to u. So our u for this case, we already identified our u to be x plus 1 and our v to be y2. So this is just going to be this is going to be u. Our u is x plus 1. Our the nv, we found that already. The nv is y sub n plus 2. So this is going to be multiplied by y sub n plus 2. And then the next one is going to be plus. So we have n, that will be plus n into the 1. That's the derivative of this, which is 1. And the n minus 1 of this, that will be, replace n by n minus 1. So this will be n minus 1 plus 1, plus 2. That will be n plus 1. So basically this will be y into n plus 1. And then the next one will be plus all of this is going to be n into n minus 1 divided by 2, and this is going to be the squared u. The square u, that's the derivative of 1, which is 0. We have this up there already, so we can just bring it here. Then we have y into n, that's n n plus 2. So this I will replace this n with n minus 2. That will be n minus 2 plus 2. That is n, and then plus so on and so forth, then plus 0. We know that this will vanish to 0. So the only thing we have left is basically this, and this is just again x plus 1 into y sub n plus 2, then plus n into y sub n plus 1. So with this, we are good to go. We can now put this into equation A where we stopped here. So we went through all of these steps just to obtain this result. So we can now put it back here to get our result. So we say that substituting, so let's say this is equation star now. Let's say this is equation star. So we now say that substituting, I mean basically this is the n of that was x plus 1 to the power, I mean multiplied by y2. Okay, this was the derivative we were trying to obtain. Okay, so we've obtained the derivative now to be this. So substituting star into a, substituting equation star into equation a. Is it a that we call this one of a? Yeah, a. So we can now put this back there. Then we will obtain the following. We will obtain 4 multiplied by this derivative. We already obtained this derivative, so this will be 4 into x plus 1 y n plus 2 plus n into y n plus 1. So close the bracket. So we substituted that. Okay, then the remaining part is plus 2 y n plus 1. So this is plus 2 yn plus 1 plus 2 yn plus 1, and then the last part here is plus pi squared y sub n. So that will be plus pi squared y sub n. You know, this is equal to 0. So we can now simplify further. When we open up this bracket, this will be 4 into x plus 1 yn plus 2. Then for this will be 4n, then plus 2. So we can say that is plus. So let's look at our destination so that we just have it in that form directly. So what we have here is 4n plus 2, so that is fine. We'll just use that expression directly. So this is going to be 4n, that is 4 times this, that's 4n, then plus 2. So both of them will carry yn plus 1, so we can say this is plus 4n plus 2 into y sub n plus 1, and then finally plus pi squared y sub n is equal to 0. And that concludes our proof. So I've been able to show that indeed this will be equal to this. So again, let's go through what we've done here. What we've done here is to identify what we have been given and see how can we get to what we are required to show from what we have been given. So this is what we are given. We were able to identify that as this expression by interpreting this y sub n to be dny. So we know that this is second derivative of y, which is the 2y, for instance. This is first derivative of y, which is the 1y. So we know that we can write it as y2, as y sub 2 and y sub 1 respectively. And then we know then that to move from this expression that we have here to this expression that we have, since we have n here and n here and n here, then we think of that already as having to take the nth derivative of whatever we already have. So when we take the nth derivative of both sides, we simplify it to see what it gives us. For this portion, we see that it carries two functions. Y itself is a function of x, so its derivatives are also functions of x. Of course, the derivatives could be 0, but then that can also be regarded as some function of x. So this is simply a product of two functions. That is why we have to take the nth derivative by using the Leibniz formula. So that's why the Leibniz formula was applicable there. For this other one, this is just a single function. This is just a single function, so we don't have to apply the Leibniz formula. We just take note of the fact that when we're taking the nth derivative of the first derivative, it will be the n plus 1th derivative. So That's basically what we used here, and it gave us what we needed. So the only thing we had to simplify was this. We did that by applying our usual method of using the Leibniz formula. So that's what we've done here, and then we arrived at the destination finally. All right. So let us consider another problem before we round off this lesson. So this will be our second problem now. So problem 2. We are told that if y equals the tan inverse of x, y equals tan inverse of x, show that 1 minus x squared into yn plus 1. This is not exactly clear. This could be 1 plus x squared, but we'll see. Anyways, um, so yn plus 2 plus 2 into n plus 1 x into yn plus 1 plus n into n plus 1 y sub n equals 0. So that's what we have right here. We are given that y is equal to tan inverse of x. So from that, we want to show this relationship. And so how do we go about this now? This is a bit different from the first problem, problem 1 that we solved up here, because in this case, in the case of problem 1, we were not given y explicitly, we were just given a derivative that relates y and its first and second derivative, okay? Which is fine. We identified what to do and we were able to do it. Now for this case, so look at this closely now. If you think of this now, you know you have y only, and then you have this expression here. This has to do with the nth plus 1, the n plus 1 derivative. This is nth derivative, this n plus 2 derivative. So we know that we should start off with a relationship that defines our second derivative, for instance, so that when we have a relationship that defines our second derivative, and possibly links it with the first derivative, or it links it with I or whatever, then we can possibly take its nth derivative. I mean, that means that for this situation now, we should seek to obtain a relationship that looks like this, a relationship that connects, possibly connects the second derivative and the first derivative, or first derivative and second derivative, whichever one we're able to easily get. So that when we have that expression, then we can now take its nth derivative, just like we did here. So this is like we are starting from, for this second problem now, it's like we're starting from ground zero. We'll first obtain a relationship like this. When we obtain the relationship like this, then we'll take its nth derivative like we did for this one. So let's quickly go through that and see. We are given y equal to tan inverse of x. So solution. So we're given that y equals tan inverse of x. So from this, we can get our first derivative, dy, will be equal to, if you like, that's y sub 1. And the derivative of tan inverse of x, we've used that a number of times now. That is 1 over 1 plus x squared, okay? And the second derivative, that's the 2y, or if you like, y sub 2. Why are we doing the second derivative? Because of this n plus 2 that we have here. We know it is when we take the nth derivative of that we're able to arrive at this. So that tells us that anyway, whether it is the relationship between the second derivative and y that we're able to get, or the relationship between second derivative and first derivative, we at least need a relationship that gets to the second derivative first before we can now begin to see if by taking the nth derivative of that relationship, that is that equation we obtain, we can arrive at this expression possibly. So to obtain the second derivative, we will use our quotient rule. That's bottom, the top. Say if this is u and this is v, we take b and then multiply by derivative of this. Derivative of 1 is 0, so that one is gone. Then take 1, multiply by derivative of this. Derivative of this denominator is 2x. That will be minus of 2x. Then divided by the square of the denominator, that is 1 plus x squared to the power of 2. So if you don't know what that is about or what we just did there, just recall that when you have y to be equal to a over b, where this is some function of x and this is some function of x, like we have it here, 1 of course is a constant, yes, it can also be regarded as a function of x. Then we know that dy dx by the quotient rule is bottom to top, that's b du dx minus top the bottom u the b dx divided by the bottom square, that's b squared. And we've examined the proof of this in the previous lesson, so you can get back there and see how we came about this. But then that's not so important if you already can remember the formula of and, which is necessary for most problems you come across here. So that's basically what we did here. We just identified that u is equal to 1 and v is equal to 1 plus x squared. And by the time you do all the necessary differentiations, you get this result. Okay. So this is our v squared. That's our v is 1 plus x squared. So this v squared will be 1 plus x squared all squared. So with this, we are good to go. Don't forget that's just what we want to do. We want to get up to the second derivative first and try to see a relationship between the second derivative and possibly the first derivative of the or the zeroth derivative. So it's obvious here that we have the first derivative to be 1 over 1 plus x squared. So for this second derivative, if we are going to relate it to the first derivative, we know it is not something we can relate with this zeroth derivative because it doesn't have a similar form to that. Okay, so but we can easily relate it to the first derivative. So we see that y2, that's the second derivative, is equal to minus 2x over this. So we can write it as, we know that this one is already 1 over x squared. 1 over x squared, 1 over 1 plus x squared, sorry. So basically this expression here is the same thing as 2x multiplied by, so we just identify how this relates with this. We see that this is 2x multiplied by 1 over 1 plus x squared, then multiplied by another 1 over 1 plus x squared. Why are we really doing this? We know this is 1 plus x squared all squared. So we know that 1 over 1 plus x squared is y1. So we can easily do that here and say that this is equal to, we know if we multiply this out, this is the same thing as what we have here, and if we multiply this out also, it's the same as what we have here. But the advantage of writing it this way is that we can easily identify that this middle term or mid term here is y1. So we can say that basically we have the relationship to be y2 equals minus 2x multiplied by y1, that's this altogether, then divided by what we have left here, which is 1 plus x squared. And then from here we can cross multiply and we see that this is 1 plus x squared multiplied by y sub 2 equals minus 2x multiplied by y1. So that's the relationship between the two of them. And from here we can simplify further by just rearrangement so that we have 0 on the other side. We will obtain the following. We will have this to be 1 plus x squared y2 plus, by the time we move this minus to this side, it will become plus 2x y1 equals 0. And so from here we have a relationship between y2 and y1, and we know that the expression we're trying to drive at now, bring out, has y sub n plus 2 and it has y sub n plus 1. Okay, it has y sub n 2, but let's see how it goes when we just go ahead with this relationship. So from here, we can try to get the nth derivative of both sides. So we say the n of all of this, which is 1 plus x squared multiplying y2 plus 2x multiplying y1 will be equal to the n of 0. And we can easily see that this is basically equal to the n of 1 plus x squared multiplying y2, close the bracket, plus this one also is a product. I mean, this is obviously a product of two functions. Y2 is a product is a function of x. This is also a function of x. So this is a product of two functions. So we have to apply Leibniz formula to simplify this. That's why I'm just rewriting it. And for this also, two we can move two out, but we have x, which is a function of x. We have y1, which is also a function of x. So we're still going to apply Leibniz formula here. But then let's write this out first. This will be 2 the n of x multiplying y1. Then this will be equal to derivative of this, whatever that is 0. So now we've gotten to the point where we now take care of each of these expressions one after the other. So let's take care of what the nth derivative of this will be. All right, so we say can identify this and say this is our equation 1. And then to find this first derivative, to find this one, the n of 1 plus x squared, 1 plus x squared into y2, we say let u be equal to, we know the derivative of this will vanish, let u equal to 1 plus x squared, and let v be equal to y2. Then it will follow that the u, the first derivative, will be 2x, and the v will be the first derivative of the second derivative, that is y3. And going further, the squared u will be equal to 2. And for this, the squared v will be equal to y4. And going further, the cube u will be equal to derivative of 2, which is 0, and the cube v will be equal to derivative of this, which is y5. And now we can generalize this. We can see that as we proceed, the nu will be equal to 0, and this will happen for all n greater than or equal to 3. And then for this, we can generalize also, because the nv will be equal to, going by this, we can see that the power here is 2 less than the power here. So basically, this is going to be y into n plus 2. So we're good to go. So if we try to expand this using our Leibniz formula, we know that it will have its first two terms, and from the third term forward, it will vanish. So by Leibniz formula, we'll have the n of 1 plus x squared. This is 1 plus x squared into y2. That's once you just get this now, once you apply the Leibniz formula, is going to be equal to, we can decide to write out the formula again and expand and expand and expand, but we already know what the first few terms will be from our previous work. Okay, to avoid that repetition, we can just use that expression. We know it is u, the nv, blah blah blah, like that. So let's just deploy that directly here. And if you like playing around with things like this, please you can do it again. But it's just sufficient to play around with it here. This will be u the n v plus this will be n into, so this will be n into the u, then the n minus 1 b, then plus n into n minus 1 over 2, then the squared u, the n minus 2b. So if you don't know what we're talking about, you can just check up there again. So I think I can still remember. That's why I'm just doing it directly. So this is n minus 2, then divided by 6. So this will be the 3u, the n minus 3b. And then the terms will continue like that. We know they are going to vanish to 0 from the third term forward. So let's just leave it right there. And let's add a new page to proceed. So this is just going to be by making substitutions now. We already know our u to be 1 plus x squared. So we'll just use that here. This is going to be 1 plus x squared. Then the nv, we already know that the nv to be y into n plus 2. So this is multiplying y into n plus 2. Then the next thing is plus n into the u. We already have the u to be 2x. So this is n into 2x multiplied by the n minus 1b. So we know the nv is y into n plus 2. So the n minus 1b, that will be y into n plus 1. Just subtracting 1 from this. Okay. Then plus the next term will be n into n minus 1 divided by 2. Then this will be the squared u. So the square u, that will be derivative of this, which is 2. Then multiplying this expression, that will be y into n. That will be n minus 2 minus n minus 2 plus 2, that's n. And plus whatever we have left here, that will be n into n minus 1, n minus 2 divided by 6. Then this is 0, that's the derivative of 2, which is 0. And then this is going to be y into n minus 1. And then it goes on like that, and it eventually gets it remains 0 through. This is also vanishing. So basically, these are the only two terms, three terms that we have left from this expansion. So we know that from here, we already know that this is going to be equal to 1 plus x squared multiplied by y into n plus 2, then plus this, that is 2xn multiplied by y into n plus 1, then plus this will cancel this. So what we have left is n into n minus 1 y sub n. So that is all we have for this situation. So let's note this as equation star. So are we close? Yeah, we're close. Are we done with all the things we need to do? Not yet. We also have to differentiate this, okay, because this is also a product of two functions. So we have to use Leibniz rule again, or Leibniz formula, to simplify this. So we go ahead to do that now. So we say that to find the nth derivative of xy1, we say let u be equal to x. We know its derivative will vanish, and let v be equal to y1. Then the u will be equal to 1, the v will be equal to y2. That's the first derivative of the first derivative, that's y2. And then we know the squared u will be equal to 0, and the squared v will be equal to y3. So basically, we know every other thing will become 0, so we can say the n u will be equal to 0, okay, for all n greater than or equal to 2. And then for this also, we identify that the nb will be equal to, you can see in all cases, this was 1, this increased by 1, this was 2, this increased to 3. And that means this is basically y into n plus 1. All right, so we have all the things we need for that. So again, to proceed, we apply Leibniz formula. So by the Leibniz formula, our dn of xy1 will be equal to, so we use those terms again, we already expanded up there, so we just invite them here. So this is going to be u the nv plus n combination of 1, that is n into the u the n minus 1 v, then plus n into n minus 1 over 2, then the squared u the n minus 2 v. We know it's become 0 from here, so there's no need to proceed with the rest. So this is going to be equal to u, our u is x, so this is x multiplying the nv. We know the nv is y into n plus 1, so let's just write it like that, and then plus n, so du, our du is 1. So this is n multiplied by 1. The n minus 1, just replace this by n minus 1. That will be y sub n. Then that will be plus whatever this is. This is n into n minus 1 over 2 squared. U is 0. And whatever this is, that is meant to be y into n minus 1. We know this is going to vanish to 0. We know every other thing will also vanish to 0. Okay, so from here we know that this is meant to be x into y n plus 1, then plus n into y n. Alright, so that is that about that. So this is the derivative of the second part. So let's call this equation star star. So now we are good to go. We now have the two derivatives, okay, that we needed to conclude on this equation A. So we can now say that we are substituting the equations star and star star into A. So that we say that substituting equations star and star star into equation A will obtain the following. So this is the equation star. We have it here. It was the derivative of the nth derivative of 1 plus x squared sub y2 multiplied by y2. So we go back here. So instead of this, we now write in or put in this expression here, which is 1 plus x squared. So we now have this to be 1 plus x squared into y n plus 2. So let's go back up there. I can't remember what those others are. Plus 2xn yn plus 1. So let's write that out. Plus 2xn yn plus 1. Then we have plus n into n minus 1 yn. So that is plus n into n minus 1 y sub n. So that is it for this first part. Then for the second part, we already know what the derivative is for this expression, the nth derivative of. So to get the nth derivative, to make use of this nth derivative of xy1, we'll have to multiply it by 2 as we have it in this expression. So that will be 2. So we go forward to make use of that result. We say this will be then 2 into what we already obtained here, which is x y n plus 1 plus n y n, close the bracket, and all of this will be equal to 0. So we can now collect like terms and just tidy everything up. So yn plus 2 appears only once, so just write that out first. This is going to be 1 plus x squared into y sub n plus 2. And then the next one, we have yn plus 1 and yn plus 1 here, so we can put them all together. This will be plus. So we have x multiplying n plus 1. We have x here also multiplying n plus 1. So this will be what do we call this now? If we examine this to this is 2x. Okay, 2x into yn plus 1. This is 2x into yn plus 1. So this will be 1 plus n into 2x into yn plus 1. So if we expand it, this will be 2x into yn plus 1, which is what we have here. And if we expand to the other side, that will be 2xn into yn plus 1. That's what we have here. And then we have plus y sub n. This is n into n minus 1. That is n squared minus n. Then we have this to be plus 2n. So this is basically y sub n into, this will be n into n plus n minus 1. That will be n squared minus n. Then this will be plus 2n, and this will be equal to 0. So from here we have this expression, which is 1 plus x squared, then y into n plus 2, then plus this expression 2x into 1 plus n y sub n plus 1, then plus this is n squared minus n plus 2n, that is n squared plus n into y sub n equals 0. So these are our relationship between y sub n plus 2, y sub n plus 1, and y sub n. So let us check, does this align with the formula expected for our final expression? We'll see that shortly. So for our final expression, we have 2 into n plus 1 x, okay, into yn plus 1, then n into n plus 1 yn. So that's exactly the same as what we got. So we just make we just write it in the format of the final expression expected from the question. So finalize our result. So we are good to go. We just say this is then 1 plus x squared into y n plus 2, then plus, so the format we have there is 2 into n plus 1 multiplied by x, then multiplied by y into n plus 1. So just a simple rearrangement. Instead of 1 plus n, we have n plus 1. Instead of having x here, we are having x here. So it makes no difference. Then for this, it is factorized in the final expression. This was n into n plus 1. So you can put that way as well. So the same thing, x squared plus n, then multiplied by y sub n equals 0. So that is that about that. I pointed out something earlier that this was supposed to be 1 plus x squared, but I wasn't sure. And that's from where we got the question. So I think it should be corrected. This question should have 1 plus x squared here, not 1 minus x squared. Okay. So we have just completed the solution. So we have now seen that indeed this is true. Okay, if y is equal to tan inverse of x. Again, just to go through what we have done together, for this situation, we can observe what we have here. It has n plus 2, n plus 1, and n. So we should expect that we should firstly find a relationship between the second derivative, that's y sub 2, and possibly the first derivative or the function itself, which is y itself. Whichever we are able to get easily, we use that. So once we obtain that relationship, which was this between y2 and y1, because it wasn't so easily obtainable with y, being that this is tan inverse of x, it doesn't have the same format as this other two. So that was why we just obtained it between y2 and y1. Of course, we know we could have obtained another kind of relationship. For instance, we could say that this was y2 equals minus 2x into y1 squared, and that will be fine, just that it will complicate the issue. Not just complicate the issue, it will also not give us a format similar to or quite similar to our destination. Okay, so in our destination we had 1 plus x squared into y something, so we expect that we should have something like that or something similar to that in our relationship that we're trying to establish. So that was why we didn't go that route. Okay, so we can give that a try, but that is going to complicate the issue. We're going to be walking about and having no solution, possibly no way out at the end of the day. So it's just good to go this way, be as close as possible to the destination as you proceed. So that's the point. That's the point for using this relationship. So once we have seen this relationship, then we know that to arrive at this, or at least something close to it, then we have to take the nth derivative of this equation. So that's exactly what we did here. And the process from this point forward is exactly the same or similar to what we did for question 1. So that is that about that. When it comes to the application of the Leibniz principle or Leibniz formula. Okay. Once you're able to identify that this is a product of two functions, that is, well, there's one part that depends on x, there's another part that depends on x. It could be y. That means in that case, of course, we expect that for a situation like this, y is a function of x. So y itself by default depends on x. So if we have x or some other function of x written together with y, we expect to use the Leibniz's formula to simplify that. All right. Thank you for watching. We'll proceed from here in the next lesson.